In this video we're going to be covering odometry. What actually is it and why do we use it? You've probably heard of the concept of odometry in terms of a car. You look at how many kilometers are on your odometer and that will have some bearing on when you should get your car serviced next and when you should sell your car and try and get the maximum return on investment. Odometry refers to essentially how far the wheels have turned and based on that the distance the car's actually travelled, or the robot's actually travelled in this case. Now this is very commonly used in robot navigation, basically because it's very, very cost effective and simple to do and gives us very good results over short distances. So most land-based robots that have wheels will use some form of odometry. Essentially what we do, we couple some encoders either directly to the motor armatures or the wheel axes or some sort of a motor shaft, and based on those encoders we can work out how far each of the wheels has turned. If we know how far each of the wheels has turned and we know the size of the wheels, we know how far the robot's actually moved. Now we've got a few different encoders available to us. We've got incremental optical encoders where we use light to just count rotations, so as it moves we have a number of slots and we see each one count through. We have absolute optical encoders as well, where we can determine a fixed angle, the fixed position of the wheel at any point in time, rather than just that the wheel's moving and the rate that it's moving at. And we've got magnetic ones as well, where we use a Hall effect sensor to count rotations based on a magnet or some ferrous material passing over this Hall effect sensor. Our most basic type of optical encoders are single channel ones. And essentially we have a disc consisting of a whole lot of position slots. Now it could be as simple as an overhead transparency that we print on and print on some black marks. It could be something that is laser etched or something like that. If we need more precision, there's all sorts of ways that these can be created. Basically, one side of the disc we have a light source, and the other side of the disc we have a light sensor, like a photodiode. As we rotate that disc, the light source is intermittently shown and blocked, and our receiver will see light, no light, light, no light, light, no light. And based on that, we can work out where we're rotating and how far we've rotated. Now, the sort of sensor that we have in the diagram here doesn't have all that many slots on it, only in the order of 20 or so slots, and so the resolution from this sort of sensor will be very, very poor. Typically, we can get high resolution encoders giving us a resolution in the order of 1,000 counts per rotation. And when they're that small, it's very hard to see those individual slots. They're really, really tiny. They're the sort of encoders that we've got on inkjet printers if you've ever taken one of those apart. Now we have a few issues with these single channel optical encoders. They're not particularly great at low velocity. We start having quantization errors, particularly when we're going very, very slow and just creeping along. They can also, one of the issues that's related, only measure rotational speed, not direction. So we assume what direction we're going based on how we're driving the motor, for example. But it just tells us that we've moved. It doesn't tell us which direction we've moved. If we get ourselves in a situation where we parked our robot on a hill like that and then turned the motors off and the robot started drifting back down the hill, we wouldn't know which way it's drifting down the hill, and that could be an issue for us. So to solve this directional issue, what we can do is add a second photodiode and LED pair. Essentially adding a second channel, a second spot that's out of phase with the first one that we can read our encoder values from. That way we have what we see there with A and B. We have one channel and a second channel, and depending on what direction that we're moving in, one channel will lead the other channel. One of the issues though is with this incremental positioning, if power is lost to the device, we have no idea where we are. And if power is lost and the device moves, we still have no idea where we are. We have no idea how many increments we've moved in between. So if we're interested in the actual position rather than the incremental count of where we're going, an absolute encoder would be used. The other thing is, adding this extra encoder or this extra photodiode receiver pair is we increase our resolution significantly. We effectively double it because we've got twice as many values that we can quantize. Here's an example of where we show one of these encoders in clockwise rotation and counterclockwise rotation as well. And we essentially see which one's the leading one. Which one has the first leading edge? Is it A, in which case we'd be knowing we're turning in a clockwise direction, or is it B, we know we're turning in a counterclockwise direction. Well, that leads to our other form of encoders, absolute optical encoders. Now, we want to use these when we're not so much interested in how far we've moved, but the rotation position is what we're most interested in. We want to absolutely know where we are. And one place these are used is in the front wheel on a tricycle style robot to know that absolute position of that front wheel. The way it's done is we have a disk that has grey coded encoded values in it, and each one is different, and I'll show you that disk in a sec. What we do is we get a light source and we split that light source and basically create a slit of light and then a detector array on the other side. So at one point in time we can measure a whole lot of clear and blocked values corresponding to a particular grey code number, and we only want to measure one slit of that at a time. Here's a grey code wheel encoder, and so we can see if we take any particular slice out of that, taking a thin slice, we'll get a grey code number, but each of those grey code numbers is separate. We know about grey code that as we transition from one to the next one, we only have a 1-bit change between each one. And so based on that, we can determine our direction as well. We know our absolute position, and based on that absolute position, we know what direction that we're actually in. So this gives us a precise position of where we are. For example, if we start up the system from scratch and we power cycle our robot that has one on its front wheel, for example, we start it up and we know the position of that wheel because we know the absolute position of the wheel. But we need this special encoder wheel, and we need a strip array of receivers to actually read all these positions all at once. Now, these optical encoders are all well and good in very high resolution, but there's some circumstances where they don't work so well. And that's particularly when we're in wet or dirty environments where we might get some rubbish that's on the optical encoder, or it might get blocked, or there's all sorts of conditions that can occur that we might not want to use an optical encoder. Now, in these circumstances, we generally use a magnetic encoder. We use something called a Hall effect sensor, which can detect whether magnetic material is placed nearby it or not. So on our shaft we can have multiple magnets, or on some sort of a disc arrangement we can have multiple magnets that pass over this Hall effect sensor. Or if we've got a metallic gear, we can even sense with very accurate Hall effect sensors the teeth in that gear to give us very high resolution. One place that I've recently used this is a robot that goes through sewer systems. Now the whole robot is rated at IP67, so it's waterproof, but the particular encoder needs to go on in the area of the robot that would be exposed. And if I used the optical encoders that we looked at earlier, it just wouldn't work. You're talking about filthy water, you've got toilet paper, not to mention all the other stuff that gets flushed down there. But having a magnetic encoder does work, because you've essentially got this rare earth magnet, or several rare earth magnets that are spinning around on the wheel, and a Hall effect sensor that's completely encased in epoxy. And they're non-contact, and they detect from a range of a few millimeters, so it does the job rather well. So we know we want encoders, but where do we actually put them? Well, we've got several options. We can mount them directly to the wheel or the wheel axle, or we can mount them directly to the motor shafts. But one thing that we can do, particularly for motors where we gear up the motors to increase our torque and slow down the speed, rather than mounting the encoder on the output shaft that actually goes to the wheel, we can mount it on the output shaft of the motor before it goes to the gearbox. Now, what does this give us? Well, if our gearbox is, for example, a 1 to 100 ratio gearbox, we'd increase our encoder resolution by 100 times. because the motor will turn 100 times for every one time that the actual wheel will rotate. And so we're effectively increasing our resolution very, very significantly. A bit of maths for the encoders, because based on these encoders and based on the pulses that we get out of these encoders, we can work out how far we've actually traveled. So what we have is CM here, a conversion factor, which allows us to convert our encoder pulses into our linear wheel displacement. And so we can multiply this by the number of pulses that we get to give us our wheel displacement. We have dn, our nominal wheel diameter, and we work this out for both the left and the right wheels. This can be something that's slightly tricky because depending on, for example, how the wheels are inflated, this diameter can change slightly. We've also got our encoder resolution, so number of counts per revolution of that encoder. And n is our gear ratio between our encoder and our drive wheel. So if it's 1 to 25 or 1 to 100 or whatever it may be. Let's go through an example. So here we've got 125 count per revolution encoder. And we mount this on a wheel with an axle, and our wheel diameter, our nominal wheel diameter, is 50 millimeters. This means that our distance per count, the distance that we actually travel, is 0.3 millimeters per count. If we took that same encoder and attached it to the motor shaft of a 1 to 100 gearbox rather than the output shaft that goes to the actual wheel, we'd increase our resolution significantly. We've got that n term down the bottom there, 100 on 1, that we multiply it by, and we get our resolution down to 3 micrometers. Much more accurate than what we had previously. So a typical robot, and when we say a typical robot, there's lots of configurations, and we'll look at these in later videos, but we'll typically have 2 drive wheels, and each of those drive wheels will be driven by a different motor. Each of those drive wheels will also have a separate encoder, so we can work out the distance traveled by the left wheel and the distance traveled by the right wheel. And it's this sort of driving that we call differential drive, where the speed of the robot and the direction of the robot is governed by the differential speed between the left and the right wheel. And that gives us this sort of arrangement where we can go forward by putting the left and right wheel forward. We can go backward by putting them both backward. We can turn to the right or left by turning one forward and one backward. And we can wheel around in one direction by adjusting the differential speed but having them both go forwards. So in terms of some maths for odometry, this really isn't all that complex. But essentially what we have is some sort of a sampling interval that we sample our left and right wheel encoders at. And we have a number of pulse increments for the left and right wheels respectively. So we might be sampling this every 10 milliseconds or so, and in 10 milliseconds we might have had 5 pulses for the left wheel, 4 pulses for the right wheel, just for example. So what we can do is we can use CM that we worked out earlier to compute the distance travelled by the left and right wheel. If we can work out the distance travelled by the left and right wheel, we can start to work out the pose of the robot. Delta U left and right gives us the incremental distance for our left and right wheel based on our N and our CM value. So how far has the left wheel moved in the last increment, and how far has the right wheel moved in the last increment? What we then do is calculate a linear displacement, which is essentially an average of how far the left wheel and how far the right wheel's moved. So we add those 2 incremental changes together and divide by 2. Then what we want to do is work out the incremental change in orientation. So B is the wheelbase, so the distance, the nominal distance between the left and the right wheel. And we say we're looking at the distance the right wheel's travelled minus the difference the left wheel's travelled divided by the wheelbase, B, and that gives us the incremental change in angle in radians. What we can then do is we can take these incremental changes in angle and incremental changes in the left and right wheel and work out the pose of our robot, the new pose of our robot. And what we do, we essentially say the new angle is equal to the old angle plus the incremental change in angle. That one's very easy. And likewise for our X and Y direction in space, wherever we are, we say the new x direction is equal to the old x direction plus the new x component that we've just calculated, and likewise for y, the old y direction plus the new y component that we've just calculated, and that's just basic trigonometry. Now we need to recognise that relative navigation, particularly in the form of odometry, isn't perfect. So one small problem that we have is when we're at very slow speeds, we have quantization error over these fixed time intervals. Where we're moving very, very slowly, we're only going to have a few counts over a time interval. When we're going quickly, we'll have lots and lots of counts, and we won't have that sort of an issue. But the larger problem is issues that occur due to kinematic issues like wheel slippage. So if wheel slippage occurs due to a bump in the road, or some uneven road surface, some wet road surface where it slips, well, the encoder thinks the wheel's moved a certain amount, but it's actually hasn't moved the robot that amount. And so these inaccuracies with kinematics, they're what we call, and we'll talk about them later on, non-systematic errors. They add up, and these, although they might be small errors, add up over time and cause a large amount of uncertainty about where the robot actually is. Particularly when these robots affect the orientation estimation of where the robot is, and they will, because if one wheel moves a fair bit more than the other one, or we think it does, but it hasn't actually moved the robot, the orientation of the robot will be thrown off. And if it's only out by a few degrees, at the start that will be fine, but as we move multiple meters out in a few degrees off from where we thought we were going, well, our distance, our displacement will be way out as well. And think for a moment about what wheeling codes would be indicating when a robot, for example, is doing a wheelie or is drifting around a corner or turning a corner where one of the wheels slips a little bit. All of these sort of issues will result in significant inaccuracies when we're using odometry for our navigation, for our relative navigation.